Hi, welcome to Venkat Varma Chemistry YouTube channel. I am Venkat Varma, your chemistry host and enthusiast, here to make your JEE, NEET and chemistry easier and more effective. Join us for short, easy to understand videos that cover key concepts, tips and tricks to ace your exams. In this session, I am going to explain alkenes in one shot. Complete alkenes in one shot. Let's begin our session. Alkenes. See, alkenes are unsaturated hydrocarbons. Alkenes are unsaturated hydrocarbons. Alkenes are carbon-carbon single bond. See, alkenes are unsaturated hydrocarbons. Unsaturated hydrocarbons. Unsaturated hydrocarbon with carbon-carbon double bonded hydrocarbons are alkenes or olefins. In this carbon-carbon double bonded, it undergoes sp2 hybridization. Its general formula CnH2n. N stands for number of carbons. Its hybridization sp2 hybridization, its geometry is trigonal planar. Its bond angle is 120 degrees. So carbon its bond length is 1.34 angstroms. The percentage of the S character in sp2 is 33.3%. In this alkenes, fullerences sp2 hybridization. Fullerences undergoes sp2 hybridization. So isomeric form of alkenes are cycloalkanes. This is for general introduction about alkenes. Alkenes are olefins, carbon-carbon double bonded. Its general formula CnH2n. N stands for number of carbons. It undergoes sp2 hybridization, trigonal planar. Its bond angle is 120 degrees. Bond length is 1.34 angstroms. Percentage of the S character is 33%. Let's move on. The general methods of preparation of alkenes. See, the first one, partial reduction of alkynes. So what is the reagent used for the partial reduction of the alkane? See, hydrogen gas, palladium, carbon, or hydrogen or palladium barium sulfate or calcium carbonate. In this hydrogen palladium barium sulfate, it is a Lindlar's catalyst. So hydrogen or nickel borate also used for the partial reduction of alkanes. See, for example, carbon triple bonded with carbon in presence of H2 gas, palladium with carbon. So here the breaking of pi bond, keeping of hydrogens. See, it forms carbon-carbon double bonded. Alkenes are formed. See, alkynes to alkenes. It is a partial reduction of alkynes. So have a look for propyne CH3, C triple bond CH in presence of reagent like hydrogen palladium barium sulfate. It is a Lindlar's catalyst. It is a Lindlar's catalyst. Lindlar's catalyst. It gives cis addition, carbon carbon double bonded, carbon carbon double bonded. See, it is alkene. It gives cis alkenes. It is a propine in presence of Lindlar's catalyst. Lindlar's catalyst. It gives cis alkene. It gives cis alkene. See, let's take another example. Butane. 2-butane, CH3, C triple bond C, CH3. The reagent, Lindlar's catalyst. Hydrogen gas with palladium, barium sulfate. It gives alkene. See, carbon double bonded with carbon, CH3, H and H. It is a cis 2-butene. Cis 2-butene. Yes, it is a 2-butane. 2-butane. Here, breaking of pi bond, keeping of hydrogens on same side. Hydrogens on same side, that is a Lindlar's catalyst. The reaction is partial reduction of alkynes. Have a look for next example. See, if we are taking C triple bond C, CH3 in presence of D2 with the palladium barium sulfate. Palladium barium sulfate. See, it gives carbon double bonded with deuterium and CH3. So it is a cis. It is a cis alkene. Cis alkene. This is the partial reduction of alkanes. Have a look for next reaction. Birch reduction. Birch reduction. See, have a look for Birch reduction. Birch reduction. It is a reagent used for the Birch reduction. See, it is an anti-addition. It is a anti-addition. So the reagent is lithium or sodium in liquid ammonia. This is a reagent used for the Birch reduction. See, if I am taking CH3, C triple bond C, CH3 in presence of sodium or lithium in liquid ammonia, it gives transalkene. It gives transalkene. 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 The name of is a 2-butane to trans-2-butene. Trans-2-butene. This is the Birch reduction. Birch reduction. See, for example, I am taking one example. See, triple bond in presence of which reagent used for the above? 3, 4, 5. See, 1, 2, 3, 4, 5. Pentane, 2-pentane. It is the 2-pentane to 2-pentene. What type of reagent used for the 2-pentane to 2-pentene? It is used for the what? Lithium or sodium in liquid ammonia. liquid ammonia. This reagent used for the conversion of 2-pentyne 2 to pentene. Have a look for one more example. Cyclohexane in presence of H2 gas, palladium barium sulfate. What is the product? What is the product in above question? What is the product? So palladium barium sulfate means Lindlar's catalyst. Lindlar's catalyst means what addition? Syn addition, means it is the same. And H. This is the product. This is the product. This is for partial reduction. Partial reduction. Coming to the next method, dehydrohalogenation. Next is the dehydrohalogenation or alpha beta elimination or anti-elimination. What type of reagent used for the dehydrohalogenation? Alkali KOH or sodium alkoxide or potassium alkoxide or sodium methoxide. We are using any type of reagent, it undergoes dehydrohalogenation. D means remove, hydro means hydrogen, and halogen, removal of hydrogen and halogen. It is a alpha beta elimination or anti-elimination. So I am taking example, see, carbon with carbon, halogen, it is the hydrogen. So carbon with halogen, the position means it is the alpha carbon, adjacent carbon is a beta carbon. In presence of alkali KOH, dehydrohalogenation, removal of halogen and hydrogen. Hydrogen and halogen, it gives alkene minus HX. Yes, it is a alpha beta elimination. Alpha beta elimination. See, I am taking one example, CH3, CH2, Cl in presence of alkali KOH. Yes, so it is a alpha position, it is a beta position. It forms what? CH2 double bond CH2. Yes, I will look for next example. See, if I am taking CH3, CH2, CH2Br in presence of alkali KOH. Alkali KOH, what is the product? It gives, it is a alpha position, it is a beta position. It gives CH3, CH double bond CH2, propene. Yes. See, in this example, if using bad leaving group or bulky base, it gives Hoffman product. Hoffman product is a major product. See, for example, I am taking example. See, CH3, CH2, CHCl, CH3. So, in this alkali KOH, so it is alpha position, it is beta position. Here two beta positions are there. Here possible the two alkene system. Yes. So first from this hydrogen, after that this hydrogen, I am writing the products. See, CH3, CH2, S, CH double bond CH2. Yes, it is a 1-butene. 1-butene. See, next CH3, CH double bond CH3. It is a 2-butene. It's a 2-butene. So, in this carbon double bonded with adjacent carbon is a alpha carbon. Here how many alpha hydrogens are there? 2 alpha hydrogens are there. Here how many alpha hydrogens are there? 2 alpha carbons and 6 alpha hydrogens are present. 6 alpha hydrogen means it is a major product, it is a minor product. Yes. So generally bad leaving group and a bulky bases, it gives Hoffman is a major. Hoffman is a major. Yes. So major. So it is which type of product? It is a CGPET product. It is a CGPET product. CGPET product. More substituted alkene is a CGPET product. More substituted is a CGPET product. See, have a look for next question. See, I'm taking question is here CH3. Yes. So it is a alpha position. It is beta. It is also beta. It is also beta. Yes. So in presence of alkali QH, what type of products are formed? See, first one is CH3 and CH2. So in this alkene system, how many alpha hydrogen? Here 2, here 2, 4 alpha hydrogen. Yes, sorry, alpha 3 plus 2 plus 5 plus 6 7. It has a 7 alpha hydrogen. It has how many alpha hydrogens? Only 4 alpha hydrogens. 4 alpha hydrogens. 3, 4, 5, 6, 7. 7 alpha hydrogen. This is the major product. This is the major product. Alpha, alpha, alpha. 2 hydrogens, 2 hydrogen, 4 plus 3, 7 hydrogen. This is the major product. What is the name of the compound? 1 bromo, 1 bromo, 1 methyl, 1 methyl cyclohexane. Cyclohexane. Dehalogenation, zinc dust, methanol, or sodium in acetone. Sodium in acetone. See, if I am taking example having halogen, it is a vicinal halide because adjacent carbons are present in presence of zinc dust in methanol CH3OH or sodium iodide in acetone. What is a product? It gives alkene. It is an anti-elimination. Is an anti-elimination. Yes. Vicinal dihalate 2 alkene. Vicinal dihalate 2 alkene in presence of zinc dust, methanol or sodium iodide acetone. So have a look for next example. See, carbon, carbon with a halogen, halogen and in presence of zinc dust forming alkene system. Carbon, carbon double bonded with ZnX2. Have a look for next example. CH3, CH, CH2, Br in presence of zinc dust. Zinc dust. Very simple. ZnBr2. It gives CH3, CH double bond, CH2 plus ZnBr2. ZnBr2. Yes. Have a look for next example. See. It is also zinc dust with methanol. What is the product? Cyclohexane. So, same as gem dihalate. It is a vicinal halide. Next is a gem dihalate. See, gem dihalate. Gem dihalate in presence of zinc or sodium iodide in acetone. Sodium iodide in acetone. Sodium iodide in acetone. It gives alkene. It gives alkene. Yes, I am writing example for this. See, gem dihalide, one carbon with the two halogen atom in presence of zinc. It gives carbon-carbon double bond. See, I am taking example ClCl CH3 in presence of two sodiums with the Cl CH3 Cl CH3. It formed two NaCl carbon double bonded with carbon CH3 CH3 plus 2 NaCl This is for gem dihalide to alkene. Gem dihalide to alkene. Next method. Fourth one, dehydration of alcohol. Dehydration. D means remove, hydration means water from alcohol. So what is the reagent used for the dehydration of alcohol? Concentrated sulfuric acid at 170 degrees Celsius. If using 140 degrees Celsius, it gives ethers. At 170, it gives alkene system. At 140, it gives ether. So phosphoric acid H3PO4, RKHSO4, POCl3, pyridine Al2O3 at 450 degrees Celsius. See, this reagent used for the dehydration of alcohol. For example, alcohol formula ROH in presence of H plus, like concentrated H2SO. For heating, it gives alkene. It gives alkene. See, I am giving one example. For example, ROH in presence of H plus. So the oxygen lone pairs are protonated. So protonated, it form ROH2 plus. Yes, ROH2 plus. It removal of water minus H2O. It becomes R plus. Carbocation is formed. Carbocation is formed. When carbocation is heated, it gives alkene. Yes. Here possible, if the carbocation is rearrangement is possible. Rearrangement means primary carbocation to secondary carbocation, secondary carbocation to tertiary carbocation. The reagent, so alkene system. I'm writing one example. Let's try to understand. Example: CH3 CH2OH in presence of H plus. So protonated, it forms CH3 CH2. So H2 plus. It forms CH3 CH2 plus. So when it's heated, it forms CH2 double bond CH2. Yes. So here there is no, it is alpha, it is beta. There is no rearrangement. It can form alkene system. So it is a elimination of beta hydrogen. Elimination of beta hydrogen. See, Have a look. For example, if OH in presence of H plus heating, what is a product? Very simple. It is attracted, protonated in the form of OH2 plus. It eliminated OH2. It form alkene system. Again, above example, see. OH in presence of H plus heating, what is a product? Same situation, protonated, elimination of water, it forms alkene. It forms a alkene. Again, one more example, see. CH2, CH, OH, CH3, CH3 in presence of H plus heating. Here OH2 protonated, it forms in the form of OH2 plus OH2. So what is a product? This is a product. CH2 CH, double bond CH3 CH3. It is alpha beta conjugation. See, conjugation dominated. Here conjugation dominates the hyperconjugation. Conjugated domination, hyperconjugation. Yes. We will look for next, if rearrangement is possible. See, if rearrangement is possible. If rearrangement is possible, what happened? So the rearrangements are phenyl rearrangement, methyl rearrangement, or hydride rearrangement. Means phenyl shifting, methyl shifting, hydride shift is possible. What type of shifting? Hydride shift, methyl shift, or phenyl shift. See, first one, hydride shift. The first one, hydride shift. So I'm taking example CH3, CH2, CH2, OH in presence of H plus. Protonated, it forms CH3, CH2, OH2 plus. Eliminated, it forms CH3, CH2 plus. So here possibilities are. There. Here two alpha hydrogens are there. Two alpha. This hydrogen I'm write like this. See, hydrogen is shifted. It is primary. Now coming to form C. CH3, CH plus CH3. It is a secondary. Yes, it is a more stable. Compare these two, primary carbocation and secondary carbocation. Secondary is the more stable. So again heated, it forms CH3, CH double bond CH2. This is our product. It is a hydride shift, hydrogen shift. Coming to methyl shift, it is a methyl shift. Coming to methyl shift, I am taking example for methyl shift. CH3, 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 CH2, OH in presence of H plus. Same protonated, it forms CH3, 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 CH2, OH2 plus. It forms CH3, 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 CH2. Carbocation is formed. This methyl shifted to this position. It forms CH3, CH3, Yes, plus charge and CH2, CH3. Again heated. Again heated. Here two possibilities are there. Two possibilities are there. Yes, see, from here first product is CH3, CH3 double bond CH, CH3. Yes, yes. In this alkene system, how many alpha hydrogens are there? 3 plus 3 plus 3. 9 alpha hydrogens are present. Yes, next CH2 double bond CH3, CH2, CH3. In this alkene system, how many alpha hydrogens are there? Here 3, here 2, 5 alpha hydrogens are there. Which is major? So 9 alpha hydrogen is a major and 5 alpha hydrogen is a minor product. This is for shift, methyl shift, hydride shift, methyl shift and hydride shift. Yes, coming to next one, pyrolysis of ester. Pyrolysis of ester. See, in pyrolysis of ester, taking an example, CH3, C double bond O, O, CH2, H. This is the ester. At 400 to 500 degrees Celsius heated. So the pi bond is shifted to oxygen and this is shifted to, and again this one is shifted to this side. So it forms CH3 COOH plus CH2 double bond CHR. This is a pyrolysis of ester. Pyrolysis of ester. Coming to next, coal-based electrolysis. Coal-based electrolysis. See, electrolysis of sodium or potassium salt of saturated dicarboxylic acid, it gives alkanes. For example, aqueous solution CH2 COONA and CH2 COONA electrolysis. C. Sodium salt of saturated carboxylic acid electrolysis, it gives CH2 double bond CH2, breaking of bond and keeping of bond with CH2 double bond CH2 with sodium hydroxide to release hydrogen gas. Here to form carbon dioxide. See, alkene and carbon dioxide at anode and sodium hydroxide hydrogen at cathode. It released at cathode. So one of the most important one, ring expansion. Ring expansion. See, ring expansion. Ring expansion. See, 3-membered ring with CH2 plus, yes, and 4-membered with CH2 plus and 5-membered ring with CH2 plus and 6-membered ring with CH2 plus. Yes, in this 3-membered cyclic ring, it has dancing resonance. It not expand, not possible in expand. See, 4-member and 5-member in these two a possible ring expansion. Ring expansion. So here a 6-member is not possible. It form hydride. Shifting of hydride is possible. So I am writing one example for this. See, for example, membered with CH2OH. Yes, in presence of H plus heated, what happened? Protonated. So same as like before, CH2OH2 plus to form a carbocation. Yes, see, 4-membered ring with the CH2 plus. It is a first position, it is a second position. Yes, the 1 and 2 positions are breaking and second position is attached with the carbocation. So the first position getting positive charge. First position getting positive charge. Yes, it is look like C same as again heated. Again heated, it forms cyclopentane. It forms cyclopentane. Yes, coming to next one. Here not possible to ring expansion. Here possible to ring expansion. Ring expansion here also not possible in ring expansion. Yes. Next. I will look for this example. I am writing. See. Writing one question. I am membered with CH2OH. In presence of H plus heated, it gives what? See. CH2 OH2 plus minus H2, it forms what? CH2 plus. It is the first position, it is the second position breaking and second position attached with the carbon, so it forms yes, it is look like this. Again heated, forms cyclohexene. It forms cyclohexene. See, I am writing next example. Six-membered with the CH2OH in presence of H plus heated. CH plus means protonated. It forms CH2OH2 plus minus H2O. CH2 plus. So first positions here, ring is not open, it has one hydrogen. This is shifted to this side. Yes, it forms carbocation, stable carbocation. In these two alpha positions are there, two possible products are formed. CH3 alkene and it is also alpha, it forms CH2, which is major. So it has how many alpha hydrogen? 3, 4, 5, 6, 7. So it has 7 alpha hydrogens. It has how many? 2 plus 2, 4, 4. Which is major? This is major, this is minor. Yes, these are the general methods of preparation of alkene system. Yes, I will look for next one. Physical properties of alkenes. Generally, alkenes are colorless, have no characteristic odor, so insoluble in water but soluble in organic solvents like benzene, carbon tetrachloride. Ethene has pleasant smell. Melting and boiling point, specific gravity increases with molecular weight. Melting point, boiling point, specific gravity increases with molecular weight. So branching of carbon increases, boiling point will be decreases. Melting and boiling point of alkenes are slightly higher than corresponding alkanes. I will look for next. Chemical properties. See, chemical properties are alkenes are more reactive than alkanes This is because of pi electrons of double bonds are located much further the carbon nuclei or less firmly bound to them. So pi bonds are weaker than sigma bond, more easily broken. Yes. Next, the reactivity of alkene. See, CH2 double bond CH2 alkene or CH double bond CH2 R2C double bond CH2. So it undergoes cis and trans. Cis is less than trans, and R2C double bond CHR is greater than R2C double bond CR2. This is the reactivity of alkenes. The one more important, stability of alkene. Stability of alkene is inversely proportional to heat of hydrogenation and inversely proportional to reactivity of alkene with hydrogen. So stability of alkene is inversely proportional to heat of hydrogenation and inversely proportional to reactivity of alkene with hydrogen. I will look for next one, addition of halogens. See, addition reactions and addition of halogen. I am writing addition of halogen. Addition of halogen, what is the reagent? So reagent uses the carbon tetrachloride. Carbon tetrachloride, it undergoes anti-addition. It undergoes anti-addition. See, I am writing one example. CH3, CH double bond CH, CH3 in presence of X2 carbon tetrachloride. X2 in carbon tetrachloride. X2 in carbon tetrachloride, it gives CH3, CH, CH, CH3. Anti-addition means opposite addition, anti-addition. The second one in H2O. H2O. First one is carbon tetrachloride, second one is H2O. So X2O means X2 plus H2O, it gives HOX. So X plus OH minus. X plus OH minus. I am writing one example. CH3, CH double bond CH2 plus HOX in presence of HO minus X plus. So what is the product? See, CH3, CH. See, so here getting what charge? Positive charge. Here getting negative charge. So here positive moves to negative, negative moves to positive. So here forms OH and X. OH and X. Let's, I'm writing one example. CH double bond CH2 in presence of Cl2 plus H2O. What is the product? So it is complete plus inductive group. This pi bond shifted, here positive charge, here negative charge. So it forms Cl plus OH minus. Yes. So it is a product. What product? It is a CH2ClOH. This is a product. This is a product. Addition of halogen. Addition of halogen. Yes. Next, coming to addition of HX. See, alkene in presence of HX, it gives alkyl halide. It gives alkyl halide. Alkene with HX, it gives alkyl halide. Yes, for example, CH3, CH double bond CH2. So the pi bond is shifted to due to the positive negative group. Here getting positive, here getting negative. So in presence of H plus, in presence of H plus, it forms CH plus and CH2 minus means it is a CH3. Again X minus, it forms CH3, X and CH3. Yes. Again I am writing one example. See, CH3, CH3 and CH double bond CH2 in presence of hydrogen bromide H plus Br minus. So pi bond is shifted. So it forms what? Here getting positive, here getting negative. Hydride shift, it forms CH3 positive charge, CH3, CH2 and CH3. Again, it is in the presence of Br minus, it forms what? CH3 Br CH3 CH2 CH3. This is our product. It is a tertiary carbocation. Yes, the previously what formed, it is a secondary. Tertiary is more stable. Tertiary is more stable. Yes. So I am writing one question about this. See, 4-membered ring with in presence of HCl. This bond is shifted. Here getting positive charge, here getting negative charge. So it forms positive charge. Yes. It is the first position, second position, cleavage of 1 and 2. So 2 is attacked with the positive charge. It forms what? You are getting positive charge. Now, this can be written as like this. Hydride shift, positive charge. It forms Cl. As much hydride as possible, it forms the product. Next, addition of H2O in H place. What is the addition of H2SO4? Addition of H2O H place. See, I am writing directly example. CH3 CH CH3 CH double bond CH2 in presence of H2O H plus. So pi bond is shifted, positive charge, negative, hydride shift, carbocation is formed, forced CH3 CH2 CH3. It is a tertiary carbocation. Adding the water H2O to form CH3 OH CH3 CH2 CH3. This is for addition of H2O in H place. Next one is the hydroxylation. Hydroxylation means oxidation of carbon-carbon double bond to carbon OH. Carbon OH is known as hydroxylation. Oxidation of carbon-carbon double bond to carbon-carbon OH is known as hydroxylation. See, addition of OH. It is a addition of OH group. Addition of OH group is a hydroxylation. So, in the addition of hydroxylation, it's possible two possible syn addition and anti addition. See, two possible. One is syn addition. Syn addition means same side addition, same side OH addition. Anti addition means opposite. Okay, so what is a reagent called dilute KMnO4 solution? Solution is it is a Bayer's reagent. Bayer's reagent used for the addition of OH groups in same side. Bayer's reagent, it is a decolorize the pink color of potassium permanganate to give brown precipitated with manganese dioxide. And again, osmium tetroxide also used for the syn addition. 1% of cold dilute KMnO4 Bayer's reagent, osmium tetroxide, OSO4 in H2O. Anti addition or CO3H biacid in H2O. H2O means aqueous, and CO3H and Ag2O silver oxide with heating it aqueous solution. It is also possible in anti addition. I am taking example. If alkene system RCH double bond CH are in presence of Bayer's reagent or osmium tetroxide, what is the product? R CH CH OH OH R. This is a Bayer's reagent. If the same alkene system to form a RCO3H in what addition? It is a anti-addition. It is a syn addition. Yes, it form RCHOH CHOH R. So again I am taking one example, one more example. See, CH2 double bonded with CH2 with silver oxide, Ag2O silver oxide. It forms epoxide CH2O and adding the water H2O. It forms CH2O. Yes, OH OH. It is an anti-addition. It is an anti-addition. OH minus attacks in this side. Yes, it is an anti-addition. Anti-addition. I will look for. See, generally, see, generally cis 2-butene, if syn addition is possible, it forms meso product. Anti-addition is possible, it gives racemic mixture. Yes, cis CSM, the short abbreviation for the cis-2-butene syn addition to form a meso product. Cis-2-butene anti-addition racemic CAR, CSM car. If trans-2-butene, if possible, syn addition, trans-2-butene, it forms what? It forms racemic mixture. If anti-addition, it gives meso product. It is very important to decide the stereochemistry of the alkene. Stereochemistry of alkene. Remember CSM car and TSR or TAM TAM. CSM car TSR TAM. Remember these things, we can easy to write the product of the alkene with the syn addition, anti-addition, stereochemistry of alkenes. Next, coming to oxidation of reactions. Alkenes are easily oxidized by oxidizing agent attacks and double bond, and the products are formed during the oxidation depending on oxidizing agent. If the combustion is present, combustion means hydrocarbon in presence of oxygen is heated. It is a what system? Alkene system. Combustion, it gives NCO2 NH2O. So CN H2N 3N by 2O2 NCO2 NH2O. 1 mole of alkene required to 3N by 2 mole of oxygen is required for complete combustion. One more important for alkene system, ozonolysis. It is a test for the unsaturation in a molecule. So in ozonolysis, it is a test for unsaturation in molecule. So in ozonolysis, these are reductive ozonolysis and oxidative ozonolysis. Remember, first write the reagent. Ozonolysis, reductive ozonolysis, reductive ozonolysis and oxidative ozonolysis. Reductive ozonolysis and oxidative ozonolysis. What is the reagent used for the reductive ozonolysis? Reductive ozonolysis, ozone plus carbon tetrachloride zinc, or ozone plus carbon tetrachloride zinc in water, or ozone carbon tetrachloride plus dimethyl sulfide. Dimethyl sulfide. This is for reductive ozonolysis. I am writing oxidative ozonolysis for reagent. Oxidative, ozone with carbon tetrachloride with H2O, or ozone with carbon tetrachloride with H2O2, hydrogen peroxide, or KMnO4, potassium permanganate in presence of H plus, or KMnO4, heat. So it is a oxidative ozonolysis and reductive ozonolysis. First of all, I am writing reductive ozonolysis. For the reductive ozonolysis, what is the product is formed? Reductive ozonolysis. For the reductive ozonolysis, for example, C double bond C, CH3, H and H in presence of ozone, carbon tetrachloride in zinc. Very simple. The breaking of pi bond, keeping of oxygen. Breaking of pi bond, keeping of oxygen. It is a shortcut to write the product. From CH3, C double bond O, H plus C double bond O, H and H. This is the product of above alkene system. Yes, I am writing next. Carbon double bonded with CH3, CH3 in presence of O3 plus CCl4 with zinc. Simply breaking of pi bond, keeping of oxygen. It forms CH3, C double bond O, CH3 plus CH3 and CH3. Again, I am writing one more example. See, cyclopropene in presence of ozone, zinc and water. Simply breaking, keeping of oxygen. Yes, to form a CH2, CHO and a CHO. Again, one more question. Cyclobutene, ozone with zinc and water. It forms CH2, CHO and a CH2, CHO. This is a way to write the product of ozonolysis for reductive ozonolysis. Now I am writing oxidative ozonolysis. Let's move on. Oxidative ozonolysis. For example, see, carbon double bonded with carbon. Yes, and H CH3 H. Yes, what is the reagent? Ozone, carbon tetrachloride in H2O. So very simple. Same double bond breaking, keeping of oxygen. Instead of H we can write O and O. Writing the product CH3, C double bond O and H. Again I am writing double bond O, H and H. Again it is heated. It forms H2CO3. It forms H2O plus CO2. Carbonate is converted to CO2 and H2O. One more example for this. CH3, CH2, C double bond CH2, C H H in presence of KMnO4 in presence of heating, breaking, oxygen keeping, and again this CH3, CH2, CH3 double bond CO completed. Yes. Now moving to C double bond OH, OH. It forms H2, CO3. It forms CO2 plus 2H2O. This is the product. This is a product for oxidative ozonolysis. Oxidative ozonolysis. Next, substitution. Allylic substitution. Alkene react with low concentration of Cl2Br2 at high temperature with NBS. NBS means N-bromosuccinamide. This is a reagent. The allylic bromination to use N-bromosuccinamide reagent. This is the structure of N-bromosuccinamide. So it is allylic substitution. We are using chlorine at low concentration, bromine at high temperature. Here also use Cl2, low concentration of Cl2, or bromine at high temperature, allylic carbon. So it is sp2, sp3 carbon. sp2 carbon with sp3 carbon is allylic carbon. Allylic carbon with hydrogen is allylic hydrogen. See, one allylic hydrogen is replaced by chlorine to form a product. It is a allylic substitution. So have a look for this example. So what is a product? See, allylic carbon. Allylic means it forms CH2Br. Again, it is allylic carbon, so it forms product. These are the product for above reaction. Yes. See, this is about alkene in complete preparation, properties of alkene. See, if this lecture is useful to you, subscribe for our channel and hit the bell icon to stay updated with latest videos and notification. Thanks for watching.